This is going to be your history of science video for the day. And so without further ado, let me pull up the PowerPoint and we will dive right in. So we are starting a new unit, which is going to be all about earth science. And this will take us for the next 4 to 5 weeks, almost up to spring break. We will be learning all about the science of how really just different aspects about the earth. It's one of my favorite topics. I think it's fascinating to look at the earth as a whole and then kind of break it down to different parts and examine those. So let's dive in. The first specific topic we're going to be looking at, I'm trying to figure out why that bar is on the bottom, there we go, is the hydrosphere. So this lesson we're going to be focusing on the hydrosphere. Now you should know what hydrosphere means, right? It means water sphere of water. And when we're talking about the hydrosphere, we're really talking about the sum of all of the water on any planet. And note here, you should have your binder with you during this video, and you should write down this definition in your science glossary section. Pause the video if you need more time to write down, or if you need to go grab your binder or a pencil. So back to the hydrosphere, you might think it's strange that it says the sum of all water on a planet when we don't think of really any other planets as having water. Other planets do have water though, and even moons of other planets have water. But Earth has the distinction of being the planet with the most amount of liquid water. And Earth is what we would call a Goldilocks planet, meaning that it is neither too close to the sun or too far from the sun. If it's close, if it was a little bit closer to the sun, the water would actually boil away. And that's what we see has happened on Mercury, for example. No liquid water could exist on the planet Mercury because it's so close to the sun that the temperatures are so hot that the water would just boil away into steam and escape. And the same thing, but like on Mars, we know there is some water on Mars, but it's not liquid water. It's all locked up in ice because it is so cold on Mars. So Earth has this, Goldilocks tendency. It's not too hot, it's not too cold, it's just right. Now, non-Christian scientists take that as a reason that is the reason that Earth is the planet on which life evolved. And there is logic to that, but I like to think, and scientists who are Christians like me like to think, that Earth is a Goldilocks planet because God has designed this specific planet to be perfect for the needs of humans. So as we will see, water is super important for life. And if you think about Thales, he thought that water was the arche because he saw that everything needed water. Nothing could live without water. So what we're doing when we're looking at the hydrosphere is we are breaking down, we're kind of isolating the water from the earth and just focusing on the water that's on the earth and on the ways that it moves around the earth, and kind of the quantities of it and characteristics of it. So first of all, let's just talk about the amount. So here it is in table form. You can see here, this is kilometers cubed. So think about a kilometer, 1/5 of a 5K length. So it's pretty long, and cubed. So that is that amount, in a cube form, a cube with all that on all sides. We can see there's a whole lot of water in the oceans. And then you can kind of go on down the list and we see that in general, the oceans have the most amount of water. Now this can be a little, data in a table form is not as easy to kind of visually understand as another form. So just for a sec, I want you to think about if you were making a graph to show this data, what would you use? What type of graph would you choose to use? Think for a sec. Hopefully you were not thinking line graph. That graph wouldn't work. You could be thinking bar graph or a pie graph. And I thought this was a cool pie graph and I wanted to show it to you. This is sort of playing on the water theme and showing that the percentage, remember how we showed that graph of air before and then the little sliver becomes the larger amount. So what we're doing here is the top graph up here is showing all of the salt water that's in, so 97.5% of all of the water on Earth is salt water. And then of that sliver, that 2.5% approximately, that is all the fresh water. And then we can see what makes up the different features of the fresh water. So let's kind of walk through this with some more specific photos. And I wanted to show you this. This is crazy. If we took all of the water on Earth and gathered it up into a ball, we would see that it's so small. It's like this little tiny marble compared to the size of our globe, which is just amazing. There's so much water, but it puts it into perspective how big the Earth is compared to us. And you'll see different numbers throughout these graphs. We're going to stick with the numbers that I have written here because that's what the source that I'm using for this uses. But so we'll define salt water as water that contains a large amount of dissolved solutes. So you should know what that means, right? A large amount of stuff dissolved in it. Now, salt water on Earth is typically sodium and chloride, but there are other things dissolved in there. And that's why when you're at the beach, it tastes a little funny because it has a lot of dissolved solutes. And it makes up about 97.25% of all of the water on the Earth. And that's why you see that large ball. That's the fresh water. I mean, the salt water. Fresh water is water that contains a small amount of dissolved solute. And that makes up about 2.75% of all of the water on the Earth. And so those two smaller balls together represent, well, let's see. The liquid, I'm not sure exactly what those two represent, so hang tight there, but the large one definitely represents all of the salt water, or all of the water. Okay, so if we think about where is the water that is not salt water, you would think, okay, there's so much water in lakes. Think about the Tennessee River, the Kentucky Lake, if you've ever been there, so much water, and that's just a little small bit of the Great Lakes, the Lake Okeechobee in Florida. All of these lakes are huge. But if we zoom in on that 2.75% of water that is, of all the water on Earth that is fresh water, the vast majority of that, about 75% of that, is actually found in glaciers and icebergs. So the majority of all of that non-salt fresh water, all that fresh water, is found not as liquid water, but in glaciers and icebergs. And we'll talk more about what glaciers and icebergs are later this week. So you think, okay, so 25% of it must be liquid fresh water in lakes and rivers if 75% is in glaciers. But no, actually, almost 25% of the liquid fresh, of the fresh water is in groundwater. Okay, so the groundwater is actually water that has seeped down into the soil and is kind of held almost like the soil and the rock underground is like a sponge, and it is held underground, and it will, if the land dips down, then we'll see evidence of the groundwater, but the ground is kind of holding water as a sponge. Now, this is why digging a well works. If you dig down deep enough, you'll start to get water. You can kind of think about it like at the beach. If you dig a little hole in the sand by the seashore, you'll get water pretty soon, right? It takes maybe like a foot down. That's because that sand is so waterlogged that the groundwater is really high right there by the beach. But every place around the Earth actually has some groundwater, and we can see it's actually a pretty big percentage of the fresh water on Earth. So it's actually 24.9% of all of the fresh water is actually underground. Okay, so that just leaves a little bit left as surface water. So we define surface water as all of the water that is found in lakes, ponds, rivers, streams, and creeks. So kind of what you traditionally think of as water, surface water. And this makes up only 0.009% of all of Earth's water. And you know what this makes me think is there's a lot of water on Earth. Because think about how much water like there is in the Mississippi River times all the other rivers, the Nile River, all these rivers. That is just a small fraction of all of the Earth's water. Okay, so when we're talking about the hydrosphere, one really big topic other than where is the water is how the water moves around. And so this diagram, I love this diagram because it has every possible way the water can move, but we're going to focus in on a few different aspects of this. This diagram is describing, you probably have heard of it as the water cycle before, and this is probably something you've learned about in lower school science. But we also can call it the hydrologic cycle. So it's kind of the way water works cycle. And this is defined as the process by which water is continuously exchanged between Earth's various water sources. So water doesn't just stay in the oceans or stay in the rivers or stay in groundwater. It's actually continually being transferred from one location to another. And that's what we're going to look at in the water cycle. So we're going to kind of work through starting with water in the ground and then ending up with it back in the ground. What are some ways that water can move through the water cycle? So let's look at first, how does water enter the atmosphere? Okay, well, there's a few ways. One way, and this, what I'm showing here could be over the surface of a lake or the ocean. We're looking at the process of evaporation. So evaporation is technically defined as, it's a chemical process really, of liquid water changing to gaseous water. Water that is in the liquid phase has molecules relatively close together. And then when it gains energy, some of those molecules escape, turning into a gas. And so when we're looking at evaporation specifically in the water cycle, we're thinking about water gaining energy from sunlight and escaping from the surface, going up into the atmosphere. So basically becoming water vapor in the air. Now another way that water can enter the atmosphere is through transpiration. And what you're seeing in this animation is actually a time lapse of clouds or water vapor forming over the rainforest, in the Amazon rainforest. Transpiration is the evaporation of water from plants. So you may have learned about this in 6th grade science with Mr. Lang. But plants have little tiny holes in their leaves, and they exchange gases with the atmosphere in that way. And one of the byproducts of photosynthesis, which is how plants make their food, is water vapor. And so as plants are kind of breathing, if you will, and doing their life processes, they naturally release water. And that's why we need to water plants, right? What plants need water, they suck it up through their roots, they take it to the leaves, and then it escapes from the leaves. Evaporation can also help cool the plants down. So transpiration and evaporation, both of these are ways that water can enter the atmosphere. Well, what happens once the water is in the atmosphere? One other thing. Why did I put this one next? Oh yes, I was going to say, speaking of transpiration, because transpiration is a way that we can lose what we call soil moisture. So the moisture that is held in the soil. Plants, by using that water and sucking the water up through their roots, that is causing the soil to lose moisture. Now, another way that the soil can lose moisture is by something called groundwater flow. And so groundwater flow is depicted here when there is a sort of a natural sort of downhill flow of groundwater down into a river or a lake, another surface water sort of body of water, that can deplete the soil moisture. So basically, if you have rain or snow fall into soil, what's going to happen to that moisture, the water that's in the soil? Well, it could be slurped up through the roots, or it could fall down, join the groundwater, and then flow off into the surface water. So both of these, transpiration and groundwater flow, are ways that the soil moisture can leave the soil. Okay, so now what happens when the water that has been evaporated or gone through the process of transpiration enters the atmosphere? So what happens is the process called condensation. And what this diagram is showing is how a cloud forms. And later in this chapter, we're going to be talking all about that. Or maybe it's the next chapter, but sometime we're going to be talking all about that. But what I want to focus on right now is condensation. So condensation is another kind of technical term and that has a specific definition in science that is a different definition than what you're probably thinking of. Because condensation in common usage, this is one of those words that has a different meaning in science than it does in common usage. To you, condensation is probably the liquid that forms on the outside of your Dr. Pepper when you pull it from the fridge, right? Or what forms on the window and that drips down, or maybe on the mirror. When the mirror in the bathroom fogs up, you're like, oh, there's like a lot of condensation on the mirror. Well, all of that has formed by the process of condensation, but what we really mean in science when we talk about condensation is a condensing, a bringing together. So remember how I said evaporation is liquid turning into a gas? So liquid molecules are kind of close together and they gain energy and they're spread all around. Well, then when the opposite happens, the gas particles lose energy, they come back together and they condense back into a liquid. And so condensation is the process by which a gas turns back into a liquid. And this is what happens when clouds form. So the water vapor that rises into the atmosphere, that's water in the gaseous state, then when it encounters a little like ice crystal or a little drop of dust, it will actually condense onto that piece of dust or onto that ice crystal and form liquid water again. So clouds are little tiny droplets of liquid water that have condensed. Okay, so once the water has evaporated into the atmosphere, condensed into a cloud, then it can re-enter the hydrologic cycle or leave the cloud by the process of precipitation. Now, you're very familiar with precipitation. You've seen it your whole life. Rain is one form. Sleet, snow, or hail is another form. For now, we'll talk about those specific types later. But for now, what you need to know is that precipitation brings water from the atmosphere, from the cloud, back down to the ground. Okay, so let's take a look at our diagram here again and kind of look at what we have talked about so far. So we have talked about evaporation, right? Evaporation is where liquid water changes into gaseous water. This diagram is calling this evapotranspiration, but that's transpiration, which is water leaving or evaporating through the leaves of plants. We've also talked about precipitation. Precipitation can fall on the land or on the ocean. Here's some more evaporation. We've talked about groundwater flow, how it can flow down underground out into a body of surface water. Here's some more precipitation. But there are a few things we haven't talked about yet. And those are surface runoff and river flow. So that's what I wanted to talk about right now. So when the rain falls, when precipitation falls, boop, 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 right here, sometimes the water will just will soak into the groundwater, stay in the groundwater, or flow out via groundwater flow. But oftentimes what will happen is that it will just hit the ground, and then flow off over the surface, either into a river or directly into the ocean or directly into a lake. So that's surface runoff, is just precipitation falling onto the surface and running into the river or the lake. And then another way that water moves around the water cycle is the flow between streams, rivers, and the ocean. So as you probably know, all rivers eventually end up in an ocean. So if we kind of follow the Tennessee River, for example, let's do the Cumberland River, which is near Nashville. The Cumberland River, I'm trying to remember all of this correctly. I believe the Cumberland River joins with the Tennessee River, which flows, just kind of curves all around the state of Tennessee, and then it flows north for a while and doesn't actually flow uphill. North isn't uphill, even though it seems like it is. It flows to the north, and then it deposits I think it's directly into the Mississippi River. I was going to say it's the Ohio, but it's not. Directly into the Mississippi River, and then the Mississippi River flows south down into the Gulf of Mexico. So if you were to dump out a water bottle in Nashville, where the river flows through Nashville, that's the Cumberland River, eventually that water, theoretically, would make it down to the Gulf of Mexico. And all rivers and all streams are like that. It's this huge network around the world of every stream feeds into a larger stream, which feeds into a larger stream, which feeds into a river, which feeds into a larger river, which goes to the ocean. And so that is another major way that water is transferred throughout the water cycle. Now, one interesting thing is that water can evaporate from, or it does all the time, water evaporates from the ocean and then rains onto the land, and it's not salty anymore. So have you ever thought about that? Why would water evaporate that has evaporated from the ocean not be like form salty rain? The reason for that is that the salt particles are too heavy to evaporate, so they just stay in the ocean. So what is leaving the ocean is actually just H2O, just pure water molecule, just water particles. And the salts are staying behind in the ocean. And so that's why we can have freshwater rain forming from evaporation over saltwater oceans. Okay, the last thing I want to talk to you about is this idea of residence time. So when we're looking at the hydrologic cycle, we're looking at how does water flow throughout all of these different sort of locations of where water can exist on Earth. And one way to measure that is by looking at the residence time, which is the average time a given particle, in this case water, will stay in a given system, in this case a portion of the water cycle. So we can see this bar graph. It's a bar graph. It's on its side, but it's still a bar graph, where we can see that what it's showing us is how long, on average, a water molecule will stay in a given portion of the water cycle. So, for example, if we're tracking, for example, one molecule in the oceans and the seas, it would take, on average, about 4,000 years for that water molecule to be evaporated and to leave the ocean. But you can see here, lakes and reservoirs, much less time, only 10 years before, on average, a water molecule evaporates and leaves that location. Notice river channels, it's only 2 weeks. Soil moisture, only 2 weeks to 1 year. Now there's kind of a pattern here. Think about this. Why do you think river channels have such a lower residence time than lakes? They're both fresh water, they're both surface water. But what's different about them? Well, I hope that you were thinking they're moving. The river channel is moving, flowing, whereas the lake and the reservoir, the water is just sitting there waiting to be evaporated. So the general pattern that we see is that whenever we have a body of water that is moving constantly, like a river or a stream, we're going to see a much lower residence time. And the larger a body of water, the higher the residence time, and also the more likely it is to evaporate, the shorter the residence time. So if you look at groundwater is deep underground, no roots touch it, no sunlight touches it. It is likely to stay there for a long time. Now, notice it says 2 weeks to 10,000 years. It could flow down into a lake or something. It could undergo that process of groundwater flow, but it also could just stay down there for a really long time. So residence times kind of give us a way to measure how fast water moves around the hydrologic cycle. Okay, here are some questions for you. Suppose you are given a sample of water taken from somewhere in Earth's hydrosphere. First question, would it most likely be salt water or fresh water? Okay, salt water is correct. If it is fresh water, where did it most likely come from? So this is like a sample of water that's just like completely randomly out of all of the water on Earth, randomly gathered. So this question is really asking, where is most of the fresh water found? Groundwater. No. Glaciers and icebergs is correct. Most of the fresh water is, like 75% is locked up in glaciers and icebergs. And then of the remaining liquid water, most of it is groundwater. If the person who collected the sample tells you it is fresh water that originally came from a liquid source, where did it most likely come from? So what is the largest source of liquid fresh water on Earth? And that is groundwater. So it would most likely be salt water. If it is fresh water, it most likely would have come from a iceberg or a glacier. But if it's neither of those and it's liquid, it most likely would have come from groundwater. Rivers and lakes, that kind of liquid surface water is some of the least prevalent type of water on Earth. Water that was originally in a plant ends up in a cloud. What two processes of the hydrologic cycle caused it to be transferred in that way? Think about it. Two different things had to occur for water from a plant to go into a cloud, to turn into a cloud. First one is transpiration, and the second one is condensation. Good job. Okay, last question. Suppose a scientist studies two groundwater sources. The first is an underground river that flows quickly into a large lake. The second is a large basin of underground water that moves at a much slower rate towards a small pond. Which groundwater source has the longest residence time? So we have an underground river that flows quickly, or a large basin of underground water that moves more slowly. Which one would have the longest residence time? Think about it. The correct answer is the second one would have the longest residence time, because the more slower moving a body of water is, the more likely it is that a water molecule would sort of live there for a long time. All right, you have watched your first physical science video for the week. Here's what you need to do now. First of all, make sure you recorded any term that I had on the PowerPoint in your science glossary. Second, you need to read these two scripture passages and then post a comment below this video describing in your own words what these passages are talking about. Okay, they are related to the water cycle, but I want to hear in your own words at least one complete sentence, good punctuation, capitalization, sentence structure, all that. Treat it like a school assignment, because it is. And that is partially to get you to think about these passages because it's interesting, but also just to make sure that you've watched the video. And then in your comment, after you talk about the scripture passages, include one question you have about the hydrologic cycle after watching the video. Okay. Again, this is just to have a conversation about this and make sure you have watched the video. Now, let me remind you, on Teams, we need to stay on topic. The purpose of this channel is to talk about this week, the hydrologic cycle and the history of science in the medieval times. So I don't want any goofiness. Stay on topic. Any comment that is off topic or silly will be deleted and you'll lose a house point. So make sure you stay on topic, be serious, be focused. Please make a new post and tag me with any questions you have about anything other than, well, anything at all. But for this video, just watch it, get your glossary terms, and do this little assignment, and then look for the next video. See you later.